Well, greetings, mathletes, and welcome back. We have two topics to talk about today, the mean value theorem, and then we also need to talk about how to find the original function if you're given the derivative. Now, the mean value theorem is an existence theorem. It basically says that if certain conditions are met, then a certain type of solution exists. Right, that's basically what it says. And so what we're going to be doing is learning how to use that theorem to show an existence, and then find the value that we're talking about in the that it happens to exist. We'll know a little more when I start talking about it more directly. And then finding the function from the derivative is actually something that we spend most of chapter 5 working on. But this is an introduction to give you kind of an intuitive feel, for you to kind of, put your fingers in the Play-Doh, so to speak, and just kind of see how it mushes before we get in there and start building stuff more directly. So in any case, let's go ahead and get started here. Okay, so the mean value theorem well, you see the word mean in there, and that's another word for average. And so really what the mean value theorem is saying, and I'm going to draw a picture first, is that if you have a function, right, and it has endpoints, and it's continuous between these endpoints, right? So you have, something that does this and back up. It doesn't really matter. It doesn't really matter what it does outside of the endpoints. This is the region we're interested in. Okay, so what it basically says is that if you compute the slope between the endpoints, right, and I'll call them A and B for convenience, right, that is your average rate of change between those 2 points. We did this earlier in the semester when we talked about average and instantaneous rates of change. In any case, what this is saying is that if on this interval you have a particular average rate of change between these 2 endpoints, then somewhere between the 2 endpoints you have a point on the function whose instantaneous rate of change matches the average rate of change. So in this case, it would be finding a point like here so that the tangent line at a point matches, right? It's actually parallel to this. So these guys are parallel. And all it says is there's at least one, right? So there could be 2. Like in this case, there's 2. There could be an infinite number of points. For example, if you had a straight line, right? Well, the straight line is its own, there's a slope to that straight line, and that's the average rate of change, but the slope is the same at every single point along the line, which means that there's an infinite number of points that meet the average rate of change. So this is basically saying, just to restate this, if you find the slope between the endpoints, somewhere between those endpoints, there's another point that has that same slope, right? That's what it says. Now, if we look at it here, so I'm actually going to write it out in math speak now instead of just drawing a picture, but the picture applies. So if f is a function and continuous on a closed interval AB, right? Okay, so that's what we have here, right? We have a closed interval AB from A to B. Then, excuse me, there's a little more. And differentiable on the open interval AB, right? So that means if you pull off the endpoints, everything in between is differentiable, right? So it's forcing it to be on the interior is what it's doing. So it's saying everywhere but the endpoints. Okay, then there exists, remember the backwards E means there exists a value C that is in the open interval AB such that f prime of c is equal to the slope, the average rate of change, right? Right, that's what we looked at in chapter, was it 2? Something like that. Is a little ways back. In any case, right, this is your instantaneous rate of change, and this is your average rate of change. And it's saying that if you have a continuous function and you can take the derivative everywhere on the interior of that interval, then the average change over the interval is represented by some value on the interior of that interval. I know I've said it a bunch of different ways. Most of that's just so that you can hear it a bunch of different ways. They're all equivalent. Whichever explanation sticks to you better is the better explanation. Okay. Okay, now using this thing. So what we want to be able to do is use this. And so I'm going to do an example of this. So let's go ahead and get rid of this. So let's say, just for fun, that I have the function f of x is equal to x squared plus 2x plus 1. And I have to be given an interval, a closed interval, and we're going to put that on the interval from 0 to 1, right? And what we want to do is show that f satisfies the conditions of the mean value theorem. In math books, it is quite often the mean value theorem is quite often shortened to MVT as an abbreviation, just because it pops up so often. There's a few of them that we do that with, and so you'll get used to the acronyms for it, or the abbreviations. Okay, so what we need to do first, right, we have to be able to find that. First of all, we need to know that this is continuous over this entire interval. It has to be differentiable on the open interval, right? That's the hypothesis. And then what we would have to do is go and find the value of c that is between 0 and 1 that satisfies these conditions. Okay, so the first thing we want to look at, well, this is a polynomial, right? We know polynomials are continuous everywhere. So we know it's continuous on the closed interval from 0 to 1. So now we have to make sure that it's differentiable on 0, 1. Right? Well, it's a polynomial, and polynomials are differentiable everywhere. So it's continuous on the closed interval, it's differentiable on the open interval. Then what we need to do is find an average rate of change for the interval given. And so remember, our average rate of change is f of b minus f of a. It's a slope, really, over b minus a. Well, we have 0 and 1 here, so I need f of 0, or excuse me, f of 1. We have to start with the high one, minus f of 0 over 1 minus 0. Right? So it's just plugging it into the slope formula, really. F of 1, if we look up here, so that would be 1 plus 2 is 3, and oh my goodness, I just realized I actually wrote the wrong function. Hold on. I missed a sign. That should be minus. Good, we haven't done any computation yet, so it doesn't affect anything. Okay, so I need f of 1, and 1 squared is 1, plus 2 is 3, minus 1 is 2. And then f of 0, f of 0, let's see, 0, 0, that makes it negative 1, so this is minus negative 1 over b minus a, which is 1. So from here, what we have is that we have 3. Okay, so the mean value theorem says that there has to be some value in between on this interval, right, from 0 to 1, that is equal to 3, right? It's an actual function value. Or not a function value, it's the value of the derivative. So let's see what we can do with this. Okay, so that's not the answer, even though we circled it. Just want to make sure we're clear on that. Now, we have, we know f of x is x squared plus 2x minus 1. The derivative of x squared is 2x plus 2, right? Okay, well, if that's the case, there has to be some place where 2x plus 2 is equal to 3. And so it's just a matter of us finding this. So we're going to take the derivative and set it equal to whatever that mean value was. So 2x plus 2 is equal to 3. So if we want to solve this, let's see what we get. So if I subtract 2, we get 2x equals 1. So x is equal to 1/2. And so this is the point. This is our value of c, right? That is equal to the average rate of change. And you'll find, too, if you go ahead and take the 1/2 and plug it into the derivative, you actually get 3, right? So x equals 1/2. Right, we just found out that f prime of 1/2 is equal to 3. You can always plug it in and actually double check. And this is the value that is equal to the mean value over that interval. And the other thing you have to check is that this value is actually in the interval. Because sometimes what you get is more than one value, especially if it's like a cubic function, so its derivative is quadratic. That means there are 2 solutions. You have to figure out which one is actually in your interval, right? Maybe both of them, but at least one of them will be, as long as it's a continuous function, right? So it tells you that it's worth looking for. It's worth your time to look for. And I want to point out, too, just why it needs to be continuous. Let's see here. We'll go ahead and get rid of that. And we'll look at a function over an interval that's not continuous. Okay, so if I have something like this, let's see here. Right, if I have something that does this, right, and yeah, I guess we'll have that. And I pick my interval from here, let's switch colors, from here to here, right? So I'm leaving the discontinuity in there, right? So it's not continuous. What ends up happening is you can end up with a slope that's negative here, but still not hit any of the things that you want to hit. Oh, actually, this is probably a better example. Let's do it this way. If I get them going the same direction. Right, so if I pick an interval from here to here, so these are equal values, this one will be easier to see. Right, the slope between them is 0. But these slopes are all positive, and these slopes are all negative, and there is no 0 slope in between. And so we have a little problem, right? Even though these have the same value and have a slope of 0, there is no an average rate of change of 0 between these two. There is no point in between them that gives you that average rate of change. So you have to be a continuous function, and it has similar problems when you have something like a cusp, and so that's why it has to be differentiable. Right? You can do the same thing here. If I pick a interval from here to here that has a 0 slope, nowhere in between these 2 points do I have a 0 slope. So you have to be real careful. It has to be differentiable, which means no cusps or discontinuities, and it definitely has to be continuous, because if you have any breaks in there, it could violate and basically not allow you to. It'll jump over values, and it may jump over the value you're looking for. So those are things to watch out for. But other than that, that's pretty much it as far as the mean value theorem goes. You're really just going to evaluate the slope between the endpoints, right? And then take the derivative and set the derivative equal to that slope and figure out what values of x will give you that. All right, so now we want to look at the second part, which is about, finding the function when you have the derivative, but you don't have the function. All right. So let's go ahead and look at the next topic here, which is excuse me, working our way backwards from a derivative back to the function. So let's go ahead and just suppose that we have a function, or we're given a derivative, right? We're told that f prime of x is equal to x squared. Okay? Now, there's some things that you can think about as you're going through these things. And we're going to go through a few of these examples. There will be set methods for this, but we're not really going to hit them until the next chapter. Right now, it's just about feeling your way through it. It gives you a much better intuitive feel for things, especially once we get to the ways to do this as, a set way, when we actually have a good method for it. We have formulas and whatnot. So if we're piecing this together, right, I'm looking at this. I know I took the derivative of something to get an x squared. Well, that's a power function, right? It has an exponent. What that means is that to get this derivative, we had to use the power rule. Okay, so if we use the power rule, that meant that this used to be, the exponent on it used to be 1 higher. So it was an x cubed of some sort, right? We don't know what sort of x cubed it was. But you notice, if I take the derivative of this, I end up with 3x squared, not x squared. So I have to do something to make sure that 3 cancels. So if I really wanted it to cancel, what I would want to have is an over 3 in here. In fact, let me put that in a different color so that, right, I'd want to be able to divide it by 3 to get rid of that. So what we can do is put a division by 3 in our original function. So it's x cubed over 3. And then just to double check, you want to take its derivative and make sure it matches up. So if I take the derivative here, I know the division by 3, it doesn't change anything because it's a constant multiple. But I can take the derivative of the numerator, which gives me 3x squared over 3, and the 3's cancel out and I get x squared. Okay, so that is one possible function that could be the derivative. Here's the problem. Let's do x cubed over 3 plus 7, right? So the question is, could that also have been the function I took the derivative of? Well, let's see. If I take the derivative here, I end up with 3x squared over 3, so I end up with x squared again, just like this. And then if I take the derivative of 7, that's a 0, so I end up with x squared. So I still end up with x squared. So what we just noticed is that there's more than one possible function that the derivative came from. So there's more than one function that have the same derivative. And it really doesn't matter what this term is if it's just a constant term. So what we do to compensate for this, and this is a way of giving all possible functions f such that f prime of x is equal to x squared, right? The way we write all of the possible functions at the same time is we write f of x is equal to whatever this term was that you found from working the power rule backwards, x cubed over 3, and then we have to add a constant because I could have taken the derivative of a constant and got a 0 there to have it cancel out. So there could have been a constant there. I don't know. If nothing else, the constant was 0, right? So we always write the plus c as far as that goes. Okay, so that's our first one. Now, let's go ahead and take a look at the next one here. So we'll go ahead and by the way, just so we're clear here, this is our answer. That's what I was trying to say. I didn't mean to jostle the whole screen like that. Okay, well, anyways. Okay, so let's look at our next one here. Let's see here. Let's do, suppose we're given that f prime of x is equal to sine x. Okay, so now we have a trig function. Now, again, you want to think about what you know about derivatives and then try to work that backwards. So you want to ask yourself, what did I take the derivative of to get a sine x? Well, if you follow that derivative cycle, right, d dx is sine is cosine. d dx of cosine is negative sine. d dx of negative sine is negative cosine. And d dx, let's put that in parentheses, of negative cosine is sine, right? So that's our cycle, and that brings us all the way back up to the beginning, right? Starts us over, which means that the function that I took the derivative of to get sine was negative cosine. I should write that as another function. It's not what f prime is equal to. So f of x is equal to negative cosine x plus a constant. Whenever you're working backwards to the original function, you always add a plus c. This is actually one of those things that every calculus teacher echoes over and over and over again because it's so easy to forget it. It's a little detail. It's not something that causes a lot of computational angst, so you don't stress about it. You don't even have to compute it. It's just remembering to write it down. And it's so easy to forget. I'm guilty of it. I may do it in this lecture by accident, even though the whole point is to make sure you remember to do it. But make sure you remember to do it. Okay. Right? And so you notice that was just a matter of memory at that point. Okay, so let's take a look at another one, and then we're actually going to back up and look at these functions one more time. That was let's do that again. There we go. That's what I need to do. Okay, so now, and let's see if you can get kind of creative with this one. Let's say f prime of x is equal to the square root of x. So let's see if you can find all, that was supposed to be two L's, all possible functions f to satisfy. Right? And functions are very satisfying. Okay, so I want to see if you can do this, right? You're going to have to be a little bit creative, but let's see what you can do. So go ahead and pause it right here and see if you can find the function that this derivative came from. Okay. Now, this is one of those places where being able to switch a root and an exponent are kind of important. If f prime of x is the square root of x, then f of x can also be written as x to the 1/2 power, right? So what that means, if we want f, I know this thing is going to have something to do with an x to the 1/2 power plus 1. And if I add 1 to 1/2, that is 3/2. So f of x is some sort of, in fact, I'm going to do the scratch over here. I have an x to the 3/2 in here. So first of all, let's just see what happens when I take the derivative, and then we can decide what coefficient it needs to have. So if I take the derivative, I get 3/2 times x to the 1/2, right? So I want to get an x to the 1/2. So I need to do something with this 3/2. I need to have something in there so that it will cancel. What will help it cancel is its reciprocal, right? So that means that the original one needs to have the reciprocal in there too. So once I piece that together, then I'm going to test it. I'm going to take its derivative and I'm going to see what happens. So that means that 3/2 is going to drop down to the front as a constant multiple, right? So the 3/2 comes out front. And then I'm going to subtract 1 from this, and 1 is the same as 2/2. So what I end up with is 1/2. Okay, so that's good. And then these cancel. Oh, that's perfect. So I get x to the 1/2. Okay, so that means that my complete original function and every representation of every possible function would be 2/3 x to the 3/2 plus some constant, right? Because when I take the derivative of the constant, it would go away. So we have to put it back in just as a placeholder to make sure we understand that it could have been something else. Okay, now, sometimes you're given enough information to actually figure out what C is, right? So what I'm going to do, since we've already taken the derivatives of these things, I'm going to go back through the functions that we just did, and I'm going to give you a little bit more information for each one of them so that we can actually go through and solve for C. Okay, so let me go ahead and clear this off, and we'll look at them again. Okay, so here's the first couple we looked at. So again, when you go through this, you're going to be given what the derivative is, right? And it says find f if f of 0 equals 5. You notice that doesn't say f prime of 0. It's f of 0. So it's actually giving you a function value. Sometimes these are called initial value problems because you're given 1 point on the function, right? The point 0.05 we know is a function value. And so that's going to give us a little bit more information and hopefully enough information to find C. Now, so we want to do the same thing we did before. We're going to figure out all of the possible functions for f of x. And let's see, we've already gone through this, so we know that this is going to be x cubed over 3 plus a constant, right? We've already worked out that much in the previous part of the problem. But if we know that f of 0 is equal to 5, what that means is if I plug in 0 for x, I should get 5 as a function value. So that means that if I plug in 5, oh, excuse me, I said that backwards. If I plug in 0, I was like, I don't remember cubing 5, plus a constant, this is going to equal 5. Right? Well, that's 0, right? That goes away. So C equals 5. And so my f of x, I actually have an actual exact function value, would be x cubed over 3 plus 5. Right? So you can actually, if you have 1 point on the function, and it actually doesn't even matter what the point is, you can always find C. Right? Now, if you have more than one C in there, which does happen later on, you actually need 2 function values. But, or a function value and 1 value of the derivative. But that's later on, and that's when it gets a little bit more complicated. But right now, we're walking into it one step at a time. Okay, so over here, so let's see, we had f prime was sine x, and we worked out that, excuse me, that f of x had to equal negative cosine x plus some constant, right? So now we have function values. And we're told that f of pi over 2 is equal to 4. Well, let's see what that does. So f of pi over 2 would be negative cosine of pi over 2 plus some constant is equal to 4. Okay, well, cosine of pi over 2. Well, you might have to think a little bit, but it's always good to look at the graph, right? And you know that's pi, and the whole thing is 2 pi. That's a tick mark, not a 1 over. And so pi over 2 is right here, which means that cosine of pi over 2 is 0. So that means negative cosine of pi over 2 is 0. So that's a 0, and I end up with C equals 4. Right? Not so bad. Good, clean fun. So all we have to do now is put it all back together. Right? So f, in fact, let me switch colors so it stands out. So here f of x would be negative cosine x plus 4 as a constant, right? And you notice if I take that derivative, I still get sine x, right? So the derivative is unique, but the function that it came from is not, right? It's kind of an interesting little relationship there. Okay, so I want to look at one more here. Let's see if you can walk through this one on your own. So I want to look at where to go. Yeah. So let's say we have f. I want to switch that. F prime of x is equal to the square root of x and let's see here. Let's say f of 4 is equal to 2. Okay. Now, we already walked through finding the function, the original function from this derivative. And what we ended up with was that f of x is equal to 2/3 x to the 3/2. Now, I just want to, and it's plus a constant. I want to point out something about this x to the 3/2. Now, when we plug things in a little bit later, it's a lot easier to look at it in terms of roots. And so I just wanted to show you a little shortcut that I've come across. Right, x to the 3/2. It is the same thing as the square root of x cubed, which can be simplified, right, because there's a pair of x's in there, to x root x. I'm going to show you a little quicker way to do it. If I change 3/2 is the same as 1 1/2. Almost wrote 1/2. 1 1/2, right? So let's go ahead and switch that. This is a nice little shortcut. So 1 1/2. Well, you almost never see these things as mixed numbers. But here's what's nice about it. If I separate this out, this is 1 plus 1/2. Well, x to the first is what's on the outside, and x to the 1/2 is the square root of x. And so if you just, now you would be able to do this a lot quicker in your head. I'm just doing it to point out how you expand things out. But basically, once you have a mixed number, the whole number part of it is the exponent of what's on the outside. So in this case, it's a 1. And then the fraction part of it tells you how to handle the root, right? It's a 1/2, so that means it's a square root of x. If it was, something like 2/3, if it was like 1 2/3, it'd be x times the cube root of x squared, right? You just switch that fractional part back to a root. So that's just a little shortcut that'll help you do it a little bit faster in your head. Nonetheless, let's go back over here now. So using that information, I'm going to rewrite this as f of x equals 2/3 x times the square root of x plus a constant. Right? And so now we just need to use this information to figure out what the constant is. So that means if I plug in 4, I should get 2 for the function value. So I'm just going to plug in 4, and then we'll see what c is. So it's 2/3, let's see, x is 4, so that's times 4 times the square root of 4 plus some constant is equal to 2. Right? So let's just see what we get here. So the square root of 4 is 2 times 4 is 8. So, and then 8 times 2 gives me 16/3 plus a constant is equal to 2. And so c is equal to 2 minus 16/3. And I'm not even going to bother with the calculator here. 2 is 6/3, right? Minus 16/3 is equal to negative 10/3. So C is negative 10/3, and that means that my final answer, I'll try that again, I was trying to switch colors there, f of x is equal to 2/3 x times the square root of x minus 10/3. Now, there's always this question about should I write this using roots or should I write this using exponents? So the first thing I want to say is both are completely 100% correct, right? If you use an exponent, that is the exact same thing as using the root as long as it's the correct exponent. However, our original problem started out with roots. And so because of that, you would kind of expect to see roots in your answer as well. That's just kind of the convention. If your original problem had rational exponents, then your answer should have rational exponents. If your original problem had roots in it, then your answer should have roots in it. You want to reflect the form of the way the problem was asked. Right? But those are the two big things I wanted to hit today. And it's one of those things. Procedurally, the steps are not complicated. What ends up causing problems is it really just depends on what function you're given. And so you have to get used to how to handle different functions. When you're using the mean value theorem, one of the things you're going to find when you're trying to find the value of C that satisfies the condition is that depending on what function you were given in the first place, you could end up with any kind of equation. The example we saw was a polynomial, but it could be a square root equation, it could be a rational equation, it could be a trig equation. And so it's just a matter of what function you get. And so you have to know how to solve different types of equations to get through this. Okay? Now, like I said, that pretty much wraps it up. And so until next time, keep your pencils and your wits sharp.